Good afternoon. It's a great pleasure to introduce Jim Hall. Jim is a professor of climate and environmental risks in the University of Oxford. Before joining the University of Oxford in 2011 to become director of their Environmental Change Institute, Jim held academic positions in civil engineering departments in Newcastle University and University of Bristol. He's internationally recognized for his research on risk analysis for water resource systems, flooding and coastal engineering, infrastructure systems, and adaptation to climate change. Jim is a member of the Prime Minister's Council for Science and Technology and is expert advisor to the National Infrastructure Commission. He was a member of the UK Independent Committee on Climate Change Adaptation from 2009 to 2019. Jim led the development of the National Infrastructure Systems Model, NISMOD, which was used for the UK's first national infrastructure assessment and in national infrastructure plans and risk assessments in many countries worldwide. He invented and now chairs the UK Data and Analytics Facility for National Infrastructure, DAFNI. Jim was a contributing author to the Nobel Prize-winning fourth assessment report of the Intergovernmental Panel on Climate Change. He's a fellow of the Royal Academy of Engineering, and from November 2021, he will become the Vice President of the Institution of Civil Engineers with a view to becoming its president in November 2024. So, Jim, it's with great pleasure that we invite you to deliver your lecture.
Thank you very much indeed, Robert, for that introduction, and to Jennifer as well. And it's a great honor to be here at the Cambridge Centre for Smart Infrastructure and Construction. It's a centre which I've admired since its creation. I really consider CSIC to be at the vanguard of the modern movement in construction and infrastructure, which embraces sensors, digital networks, automation, computation. And implementing the CSIC vision in the construction sector means, amongst other things, a revolution in the nature of civil engineers, which I am, as you've just heard, who we need to become as adept with the digital and the electrical as we are with the mechanical properties of materials and structures. It's a vision that Lord Mayor, as you've just heard, set out in his presidency of the Institution of Civil Engineers, and it motivates the institution's current motion to create a new professional qualification of the Chartered Infrastructure Engineer, which I hope all of you who are members of the ICE will vote for when it's put to a ballot to members in the early next year. Today, however, I'm going to take a step back from the beams and columns, tunnels and slopes, which characterize infrastructure systems. They form the cells and organs of infrastructure. But I'd like you to get in a metaphorical helicopter and zoom up in the air to look down on how infrastructure systems operate as networks to deliver services to people and economies whilst traversing the natural landscape and dominating the Earth systems. The research and analysis that I'm going to talk about today studies infrastructure systems at large spatial scales and often looks decades into the future. And we're interested in how infrastructure assets operate together to deliver services and how that varies over a range of different timescales. As we look down on the transport and energy and water networks in the photo, we can see a static snapshot. But we know that the services that these systems deliver vary on an incredibly wide range of different timescales. From our helicopter, we might just spot that the road network becomes more congested during peak hours. And if we look down on a reservoir, we might see it, and this is Cape Town, during the drought, emptying and filling in response to periods of low rainfall and increasing demand for water. As we look out over sea in recent years, we'll see a proliferation of wind turbines and recognize how sometimes they're spinning like crazy and at other times they're stationary. And the proliferation of electric lights at night, and they're largely being switched off during the day, will give some impression of the fluctuations of energy demand, which clearly not synchronized with the availability of electricity from those wind turbines. I'm possibly laboring this point to emphasize how important variability in space and time is to the performance of infrastructure systems. Properly characterizing that variability is fundamental to the analysis of infrastructure systems. A version of variability we're particularly interested in is performance of infrastructure during extreme events. These events, by definition, occur rather rarely, so we have relatively little information about them. They may be due to human shocks like terrorist attacks, industrial accidents, or shocks on the demand side, like the COVID-19 pandemic has been. Or they may be due to environmental hazards, geophysical shocks like earthquakes and tsunami, or hydroclimatic events like floods, cyclones, droughts, and wildfires. These events populate the tails of the distribution of day-to-day variability. And to begin to think about how we go about characterizing this and how important that is, let me dive into some analysis that I did with Ed Byers at IASA, the International Institute for Applied Systems Analysis, to look at the risk of droughts causing cooling water shortages at power plants, which then has a risk of impacting the availability of electricity supplies. And in order to analyze that problem, we had to look at the probability of low flows in rivers at where there are power plants on those rivers which use fresh water to cool the power plants. We then had to look at the variability in energy demand, because one might start thinking about this problem and saying, well, what's the likelihood of there being a low flow at a particular power plant? But power plants are all connected together with the transmission grid into a network. And usually more than one power plant is off the grid at any point anyway. So what really matters is what's the probability of there being multiple cooling water shortages at the same time as high electricity demand, which we're characterizing here in terms of fluctuations in energy prices. And by putting those things together in a model which is both spatial and temporal in its characterization of variability, we could look at the very bottom of this diagram here at what is the potential financial impact of those cooling water shortages. And the expected impact is relatively small because they're rare, but it could be really quite significant in terms of millions of pounds per year. It's small compared to the overall variability in energy demand, which is depicted by this seasonal profile on the energy demand, but it is by no means significant. And in order to characterize that, we had to put a number of different, really quite different pieces of analysis together. Now, the example I've just given involved dealing with variability in space as well as time, but to really illustrate the importance of this point about spatial dependence, let's look at some extreme floods in this work by Rob Lamb, Jonathan Thorne, and other, and I see Rob is on the call today. And this looks at some actual observed floods. And what we see from these really big floods is that they extend over quite wide areas of the country at the same time, but they don't extend over the whole country. So to properly characterize that flood risk, we would need to understand this question of spatial dependence. And during the 2016 Flood Resilience Review, which I was advising, this became known as the Oliver Letwin question. Oliver Letwin was Chancellor of the Duchy of Lancaster at the time. And the really quite common sense question from Mr. Letwin and others was, well, surely we're seeing quite a lot of 1 in 100-year floods at the moment. And the point there is that to understand how likely that is, you need to understand spatial dependence. If one was only looking at one river gauging station, there are 900 odd gauges in this diagram, the probability of a 1 in 100-year drought being exceeded in any given year, or the probability, if they were all dependent, fully dependent upon that, of it occurring would be 0.01. If each of those 900 points on rivers were independent, you'd have a 900 odd throws of that 100-sided dice, and the likelihood is that in any given year, somewhere was bound to have a 1 in 100-year flood. But what the proper characterization of spatial dependence tells us that actually anywhere in this country, there's probably in any given year, there's a probability of about 0.8 of a 1 in 100-year flood occurring anywhere in this country. That's really important. And what's also important, of course, is how climate change is influencing those probabilities. These are 11 different climate model simulations of what will happen to to a relatively high flow, a flow which is at the 90th percentile or is not exceeded 10% of the time. And you can see some very different patterns for how climate change is predicted to influence those floods in the future. So we really need to look at analysis methods and systems that are robust to those uncertainties, that can cope acceptably well in a wide range of possible futures. So that's a look at the hazards. But when then extreme events occur, our infrastructure systems are subject to extraordinary loads, leading to damage, possibly both impacts on the operation of the assets. If the foundations at a rail bridge over a river are subject to scour during extreme river flows, as illustrated here, it might be necessary to impose speed restrictions or to stop the trains using the line. And we think of these, of the structural response to these loads also in probabilistic terms, in terms of a conditional probability of failure given the severity of the flood event. And for this piece of analysis, also with Rob Lamb, we had a remarkable data set from Network Rail of 100 observed bridge failures in the space of more than 100 years. And for some of those bridge failures, we had an estimate of the flow at the time of those failures, which is really useful information. And that enables one to construct the blue line in the center of this diagram. There were quite a lot more other bridge failures where we didn't know what the flow was at the time of failure. And if you include those in the data set, the picture of the fragility, the conditional probability of failure actually gets even higher. That's the gray line, which has moved leftwards. But then what one needed to recognize is that most of the bridges in this data set had never failed and had been subject to extreme loads and had actually stood up. And when you include those survivors in the reliability analysis, you end up with the curve on the right, the red curve, which gives what we think is the most realistic general estimate of this conditional probability of bridge failure given flow, and a more reassuring estimate, though the uncertainty bounds are significant. And as we've seen from the historical record, the bridge failures do occur from time to time. But if you're thinking about risk to the rail network, what the possible impacts are, you don't just need to look at the probability of failure, but also to look at what are the rail flows, the numbers of trains and passengers going along the network, which is the left-hand panel here. And then also what's the possibility for rerouting. By putting together the connectivity of the network with the amount of flows, as part of the Transport Resilience Review, my colleague Raghav Pant devised this index of points on the rail network where a failure would have the most disruptive impacts. We can do that kind of thinking in electricity power networks as well. So how might failure of some electricity power assets, supply substations, lead at one point actually trigger cascading failure when the power grid does not have enough capacity to reroute the power flow. And so failure at one point can trigger excessive demand at other points in the network. And at this point in our story, this actually is a figure from the 2003 electricity network in the Northeast USA, which was a prime example of that type of cascading power network failure. But at this point, we then need to acknowledge the existence of interdependencies between different infrastructure networks. The fact that practically every system these days depends on electricity, telecommunications, and also actually on transport for accessibility of people who operate the network. And so because of these interdependencies, the possibility that failure can propagate from one network to the next, which was something in this analysis, Scott Thacker and colleagues looked at the criticality of major electricity assets, not only in terms of the number of people who are dependent on those assets, but also the number of other infrastructures which are dependent upon them, and hence the total cumulative number of people that could be disrupted due to infrastructure failures. And that work was taken forward with the National Infrastructure Commission, where we looked at a vast number of scenarios of these cascading failures, which you can see here, where failure in the electricity network propagates back into the electricity network, but also across into the telecoms and transport networks, and possibly back again into the electricity network. And within that analysis, we then looked at if you added just 1 additional degree of redundancy of connectivity in that network, to what extent could you curtail all of these interdependent failures, which is the difference between the upper diagram and the lower diagram there. Another interesting question we looked at was if you put further backups into the power system, how much could you reduce? So the y-axis in this diagram is the number of avoided customers without power you might achieve by introducing more backups into the network. The combined effect then of failures on one or more infrastructure network is that people or businesses will be without access to the infrastructure services upon which they depend. Homes and factories may be without power, water, digital communications, workers might not be able to travel to work, or factories may not be able to get supplies by road, rail, ports, airports that they need to continue production. They may have some stocks, inventory, but in today's just-in-time world, inventories are kept very slim. And these business interruptions will affect economic production, and will also have so-called upstream and downstream economic effects. upstream in the sense that disrupted businesses will no longer be demanding goods and services from their upstream suppliers, and downstream in the sense that their customers will be deprived of their products. And there'll also be an economic impact on final demand, both during disasters when households might curtail their economic activities, whilst they might spend more in the construction sector on repair of their damaged homes after the disaster. And in this piece of analysis with Elko Cox, we looked at some electricity substation failures in the southeast of the country. And then in these different scenarios, because of those supply chain interdependencies, you can see that in the most disastrous catastrophe in the southeast of the country, there are impacts in widely across the UK. Whilst on the right-hand panel, we began to look at how after a disaster on day one, what the sequence of getting the network back up and running and enabling an economic recovery, so that all of the red and pink on the picture goes away, how that sequence might actually happen. And then putting that together for the Environment Agency as part of their long-term investment scenarios, we made this quite important point that, first of all, lots of infrastructure is in the floodplain. About 80% of infrastructure assets are either directly at risk of flooding or indirectly at risk because of interdependencies with infrastructure which is in the floodplain. And then if you look at how many people are dependent on that infrastructure, about 20 million properties are dependent upon infrastructure which is either in the floodplain or itself dependent on infrastructure in the floodplain. And so that's almost 10 times more than the number of properties which are actually in the floodplain. Now, the impacts of flooding on those properties are quite different, aren't they? If your property is subject to flooding, you can imagine what all of those impacts are. Whereas here we're talking about homes being without power because a substation has been flooded, or without water because the water treatment works has been flooded. But nonetheless, this was a significant addition to the Environment Agency's analysis of the risks of flooding and the case they made to government in terms of the need for investment in flood risk management. And then looking more broadly, we've seen these business interruption effects in the Thailand floods, where there was 25% of the world's hard disk production in Thailand. Western Digital, for example, had major disruptions to its supply. Toyota had a whole series of parts being produced in Thailand. Toyota's insurers apparently didn't even know about this, and yet Toyota lost about 20% of its production during the quarter when the Thailand floods occurred. And we've analyzed those types of cascading failures across countries, looking at typhoons in Vietnam and the ways in which the economic impacts propagate into neighboring countries. And in this work still in review, led by one of my doctoral students, Jasper Verschoor, we've looked at all of the major ports in the world, and Jasper has done some fantastic work with automatic ship identification data to understand how many ships and what types of ships are going through these ports, to establish the criticality of those ports with respect to imports on the left and exports on the right. And so how interruption at those ports might then propagate through the global economic system. So to summarize the types of risk we're talking about here, we started with the direct damage to infrastructure assets, and that would require repair or replacement of those assets if they occur. Then there's the lost revenue from disruption of infrastructure services. Then there's the broader business interruption to infrastructure users. Users are people who depend on electricity, water, digital communications, for example, interrupted production at factories. Then the knock-on effects through supply chains, upstream and downstream through industries and consumers. And then a final category, which I haven't had time to go into, though we've also analyzed and modeled this, is the possibility that repeated catastrophic events can damage business confidence, impact on investment, and impact on the public finances of countries in a way that, in particular, poor and vulnerable countries can get trapped in a poverty trap where they never really have the capacity to recover from disasters before the next disaster comes along and again does massive impact on their economies. So now let's begin to think about the responses, and we can think about them in broad terms, in terms of ways of enhancing resilience. And resilience we think of quite conventionally in terms of the capacity to resist shocks. So how can we reduce the scale of hazards, strengthen systems so that they can resist those hazards better, to cope during shocks, to recover and restore services as soon as possible after a shock, and then a capacity to learn and enhance the system going forward, so that one, to coin the popular term these days, builds back better. And in the many ways of doing that, of enhancing resilience, many versions of how it's done in practice. Here are a few examples of how one might improve the resistance, the strength of infrastructure assets, in this sense, road infrastructure in Vietnam. And one needs to look at not only the benefits of those interventions in terms of risk reduction, but also the costs of doing so, and whether that cost is actually affordable and proportionate to the benefits of risk reduction. And in this picture here, using data from the World Bank, one sees that building climate resilient assets can be quite an expensive business. So there's a trade-off here. At the bottom of this picture, the costs, and of course we need to think about cost in whole life terms, the initial upfront investment, the ongoing maintenance, maybe occasional periodic maintenance, and that has to be weighed against the benefit, which is the risk reduction associated with investment in adaptation. And as we expect risks to increase in future, we would expect those benefits to increase in the future as well. And so my colleague Raghav Pant, who's been responsible for a lot of this analysis, has applied this in Vietnam, amongst other places. Apologies for the slightly small picture on the right, but it's really quite important, because the y-axis there is the benefit cost ratio of every possible intervention in the transport network in Vietnam. And then, so the ones over the red line are the ones which are cost beneficial, have a benefit cost ratio greater than 1. And what you can see from this is that there are thousands of assets there where actually investing in resilience is not affordable. This is an enormous transport network, but there are many assets where it definitely is affordable. So this is where one should be focusing and targeting investment in order to maximize the economic benefits for Vietnam as this country develops going into a climatically uncertain future. And of course, there are uncertainties, many of them, sensitivities in that type of analysis. And in this diagram here, also created by Raghav, we're looking at roads at the top, bridges in the bottom panel. And the color scale here is how many assets are economically viable to do this type of climate resilient upgrade to. And that number is very sensitive to a couple of very interesting parameters. One is the duration of disruption. How many days does it take us to get this bridge or this piece of road back in action again? And that's really important because the scale of these wider economic impacts depends on how quickly you can get the traffic flowing again. But you can imagine that's a very uncertain number. And then on the y-axis on these diagrams is the scale of economic growth. So how much economic activity might be impacted and how's that going to grow in the future? And if in a country like Vietnam, we're expecting the economy to grow pretty rapidly in the future, then we can make the case for investing a lot more in adaptation because it's going to pay off in the long run. So to recap on all of this calculation, we're taking hazard layers, as I say, paying a lot of attention to the spatial dependence in those hazards, combining it with infrastructure networks to identify places in the network which are particularly vulnerable to those hazards, looking at how failures in the network can lead to disruption to the flows on those networks, and then using economic modeling to understand the wider economic impacts of all of those disruptions. And as we've said, the benefit of risk reduction is the marginal reduction in risk comparing where the risk if we do nothing with the residual risk, that hopefully much smaller risk that's left once we've done something. And that has to be weighed off against the cost of strengthening a particular part of the network. That is hopefully all clear. I've referred to decision makers. Who are these decision makers who want to know the costs and the effectiveness of various options for reducing risk in the network? And the answer is, and in a sense, this is good news in that we have many customers. There are many people who want to know that have this type of information. To start with, there are engineering designers. In engineering fields, the notion of risk-based design, that one should be setting design standards based on the amount of harm that you can avoid, has existed since the middle of the last century. That's why I'm showing these two photos of the pioneers of this type of thinking, Alfred Freudenthal and Alan Cornell. And a seminal version of this risk-based optimization of flood defenses was done by the Dutch economist Arthur van Danzig in 1956. And in this view of the world, the optimal design of a structure balances the marginal cost of further strengthening of the structure, for example, by raising the flood protection a bit higher, with the marginal consequential benefit of risk reduction. Versions of that type of analysis are done in practice, especially for flood defenses, at least approximately. But for the most part, engineering design is more dictated by codes and standards. So that type of explicit risk-based optimization is seldom carried out. Then risk information can inform asset management decisions, where, when to invest in maintenance or repair of infrastructure systems in order to ensure efficient service provision. Spending on maintenance and repair will improve the condition, delay the deterioration of physical assets, hence reducing the probability of failure and the associated risk. And the risk-based asset management problem involves balancing the beneficial risk reduction with the cost of maintenance and repair. And it's a very difficult problem because we need to understand the effect that maintenance will have on rates of deterioration and we need to be able to relate the observable characteristics which one sees during the inspection of assets with their probability of failure. And this kind of rigorous probabilistic approach to maintenance has been applied in relatively few very important structures, like the Eastern Scheldt storm surge barrier in the Netherlands, where the late Jan van Noordwijk and Han Breiling worked on a very elegant solution to that problem. And on the left, on the Thames tidal defences, colleagues and I have worked both on flood defence deterioration and risk-based asset management. The application that has come to much greater prominence in recent years has been the use of risk information for investment prioritization. So the exam question that's being asked in this context is how to deploy a limited amount of resource across a system in order to maximize the benefits of risk reduction. And that's a question which is being increasingly asked by development banks, large utility companies, regulators. Here I'm showing a snapshot of Thames Water's water resource management plan, which we did a lot of analysis for. And here they're navigating a version of the what in the energy systems they refer to as the trilemma, balancing the reliability, or on the other hand, the risk of system of security of supply with cost. So that's exactly the optimization trade-off I've been talking about. But then for the third part, with environmental impacts. And in this rather neat depiction by Thames Water, they've shown a series of different investment plans, how they perform with those three different criteria: cost, environment, and resilience. Here they say cope with future challenges. And then they've come up with a proposed compromise, best of all worlds maybe, solution. And another application for this type of information, which has come to the fore really quite recently, has been the increasing demand for physical climate risk reporting by investors. The G7 meeting in June this year agreed to mandate climate reporting in line with the recommendations of this report here from the Task Force for Climate-Related Financial Disclosures. And there's now a flurry of methodologies being proposed for reporting physical climate risks to financial assets. Though if they consider risks from infrastructure failure at all in the way that I've been describing, they do it in a very rudimentary way. So there's a real opportunity here to inject more analysis into a really important part of thinking within the financial sector these days. And the insurance sector has confronted similar issues. And in many senses, the insurance sector is at the forefront of modeling natural hazards to large spatial portfolios of buildings and businesses. It wasn't always thus. Before the 1990s, insurance premiums were based on actuarial estimates of losses in the past, but Hurricane Andrew in 1992 led to unprecedented losses, and so insurers began to worry that looking in the past was not a good guide to the future, and adopted so-called catastrophe modeling, CAT modeling. But CAT modeling doesn't include the infrastructure and network effects that I've been talking about. But now, led by the multilateral development banks like the World Bank, there's an increasing interest in new disaster risk finance and insurance products, especially for sovereign governments, because what they're interested in here is that big catastrophes lead to large-scale infrastructure failures, which put massive demands on the public finances for repair and reconstruction. They also impact tax revenues. When that happens, countries struggle to service their debts, and they will impact upon their credit ratings. So the World Bank, the IMF are very interested in how can we analyze the scale of these infrastructure risks so that we can put in place disaster risk finance and insurance mechanisms like parametric insurance and contingent insurances to support the fiscal stability of countries which are increasingly exposed to physical climate risks. And sorry, that was related to what I've just said. And then finally, this is coming to intense visibility in the build-up to the COP26, the UN Climate Conference, where, of course, most of the attention will quite rightly be upon countries' commitments and actions with respect to mitigating greenhouse gas emissions. But the UK government is also leading and partnering with the so-called Race to Resilience. Resilience and adaptation will be one of the foci of COP26, as it will be within the finance day of the negotiations. And so the types of capabilities that I'm talking about here are feeding into a series of contributions to COP26. The first is around development of transferable national tools for infrastructure risk analysis and adaptation prioritization. And my team are leading development of that tool in a pilot in Jamaica with the Coalition for Climate Resilient Investments and FCDO. As part of a very interesting initiative called the Coalition for Disaster Resilient Investments, they're going to launch an international survey being done primarily by researchers within my team to look at the softer aspects of infrastructure resilience, the design standards, regulation, enforcement in a whole range of different countries to try and understand how that varies from country to country and what influence it has on the reliability of infrastructure systems. And then we're working with support from the Infrastructure for Development Forum and a series of other partners to develop this global analytical capability for looking at systemic climate risks from infrastructure. And that framework, which is being developed at a global scale, follows very much the framework which I've been through already, combining natural hazards, networks and the connectivity of infrastructure assets, analysis of the exposure of those assets, looking at the vulnerability, their sensitivity to hazards when they occur, and then looking at the services that are delivered and the wider economic impacts of failure. And so that provides information on the risk of direct and indirect losses worldwide, the macroeconomic impacts, and helps to identify adaptation options and benefits. And we're in a remarkable position now, being able to do this type of analysis on extraordinarily wide scale, which in a sense, it's been a long time waiting, but takes me to the title of today's lecture, because of this recent proliferation in globally available data sets and the existence of the computational capabilities to analyze those data sets. So there are a number of products for looking at fluvial and coastal flooding and storm surge risks, for looking at cyclones, heat waves, wildfires, landslides, droughts. Those were brought together in a global scale analysis already led by Elko Cox when he was working within my group, which became part of the World Bank's flagship report called Lifelines, which looked at the exposure of transport networks to natural hazards on this sort of spatial scale all the way around the world. And you can see exposure to cyclones, earthquakes, surface flooding, river flooding, coastal flooding in different low, middle, and high income countries, and how that exposure varies depending on the scale of the wind speed, peak ground acceleration, water depth. Then alongside those global hazard data sets, there's a really exciting developments in global infrastructure networks. The most widely recognized of these is the development of OpenStreetMap, which enables us to analyze road network exposure to climate-related risks anywhere on Earth. I've already referred to Jasper Verschoor's work on port assets. There's a tool illustrated here called Grid Finder, which we contributed to the development of with the World Bank, which generates synthetic electricity transmission grids in every country on Earth. It's pretty well validated in about half a dozen countries. And so by doing this, you can begin to get realistic patterns, and some of them real patterns of where electricity transmission networks are on Earth. And so you can begin to analyze their exposure, for example, to hurricane, cyclone impacts, which would bring those networks down. And so on through the infrastructure assets, and then also a proliferation of data for looking at the human impact, both people, economies, and some information around infrastructure costs. Now, there are a whole series of gaps in our knowledge associated with those things. Our knowledge of climate-related hazards and how they're changing, the asset information, in particular around asset condition and fragility, asset usage, the costs of repair and reconstruction. And some of those gaps are going to take a long time to fill, but we're in many senses in a remarkable position. And just before I close, I wanted to give an example of how this is, has been put together. So I need to share my screen again.
Here we can see each of the infrastructure networks. The electricity transmission lines in the power grid, railways, and roads of different classes from trunk roads and motorways to primary, secondary, tertiary and other roads. If we zoom right in, then we can see the fine detail at the urban and neighbourhood scale. Here we can see the three categories of hazard at a 100-year return period. The darker colours are indicating higher flood depths or wind speeds. We've got coastal flooding, fluvial flooding, and cyclone gust speeds. If we hover over the map, we can see the depths and speeds at different points. If we click for more information, there's a brief description of the full set of hazard data used in the analysis across fluvial and coastal flooding at different return periods, climate scenarios and future times, and cyclones at a wider set of return periods but only under historical conditions. If we zoom in, then we can see the resolution of the grid cells in the underlying data sets, and we can hide and show layers to see where they might overlap. The 3 sector-specific pages show roads, rail, and electricity, each showing the results of the risk analysis for that sector. In each of these maps, infrastructure assets in light yellow are at lower risk, and the range goes through orange to dark purple for assets at the highest risk. Any assets in grey have no exposure to the hazards we considered in this study, so no risks were calculated. The expected annual damages are the costs of rehabilitation or reinstatement of damaged assets combined with the probability of failure. The expected annual economic losses are the macroeconomic losses associated with disruption of all services provided by that asset combined with the probability of service disruption. And then the total risk is the sum of expected annual damages and expected annual economic losses, where we assume a flat rate of economic loss per day of disruption and a disruption length of 30 days. This page shows a Vietnam case study where we show the results of a previous national scale project.
So thanks to Tom Russell, who was the lead developer of the interface there and was doing the voiceover. And as I say, there are lots of gaps in that analysis. I'm first to own up to that. And there's a lot more work to get it properly validated. But this is the direction of travel. And we're now really in a remarkable position to do this type of analysis, to generate quantified spatial analysis of climate-related risks to infrastructure networks practically everywhere on Earth. And within that, we're generating estimates of economic losses and risks at present and in future scenarios, and that forms the basis for making the business case for investment in resilience and adaptation. This work is highly spatial, as you've seen, so we can attribute that risk to assets within the infrastructure networks, which enables that prioritization of resilience planning and engineering design, asset management, and finance for those interventions. And this work is intentionally open and accessible. The platform I've just shown you is available on GitHub, as is all of the source code which we use for doing our analysis. And we're, as far as possible, using openly available global data sets. And that's really important because it builds trust and it helps to build capacity within the many countries that we're working in, so that people can take on this type of analysis and do it for themselves. And a much wider group of people can become engaged in these really crucial questions about the risks to and resilience of the systems upon which they depend, and become more engaged in a more democratized version of decision making. And with that, I'll leave it there and be very happy to answer any questions.